We've been slowly making our way through chapter 8, which is all about cumulative damage in high cycle fatigue, and accounting for different factors, and then even using some of what we knew from linear elastic fracture mechanics. And so we've gone through quite a bit of different phases of failure. And so today I thought I would just do the end of the example problem at the end of chapter 8. Solve that two ways. They only solve it one way. And then also do one of the problems at the end of chapter 8 involving the rain flow counting, so you can get a full example of that. And so it should be sort of a easy to digest lecture. There's some math, there's some drawing. So that's kind of what we're doing today. So the problem at the end of chapter 8 pen is not responding. Has to do with a plate with an edge crack in it that has been discovered using non-destructive inspections. Oh, what is happening with this thing? Ah, there we go. So I've gotten one little thing to show up, but not like enough to write with. So I'm just trying to see if it'll come back. Okay. Try changing the battery again. This is the example at the end of the chapter. Yep. So it's section 8.8, using the ideas. Okay. So they give us this problem. They say, suppose that a 1/2 inch thick plate, 10 inches wide and 30 inches long, so 10 inches here, 30 inches long, and the thickness is 1/2 inch. Okay. Used as a tension member in a high performance structure, undergoes released loading. So that means it's loaded and then back to zero. Released tensile loads. Okay, so they go this way, right? And they distributed from 0 to 160,000 pounds parallel to the 30-inch dimension. So that's how I drew it here. So load P goes from 0 to 160,000 pounds. An inspection has discovered a through the thickness crack at one edge near the midspan of the plate. So that's what I drew, that tiny little thing right there. So we're going to say A is equal to 0.075 inches. That's what the dimension of the crack is estimated to be. The material is a nickel, molybdenum, vanadium steel. We kind of looked at some plots that had that material already, with a yield point of 84.5 kpsi and plane strain fracture toughness of 33.8 kpsi square root inches. And crack growth, we looked at a chart with a bunch of points on it that showed how these cracks grow in the steel, kind of that gave us an idea of the DADN, right, crack growth rates, as a function of the change in their stress concentration. And so it says, an estimate is to be made, so that's our job, of the remaining life in cycles before catastrophic fracture of the structural plate occurs. So we're past the phase of cumulative damage. Is this going to get a crack in it? It's already got a crack. So therefore, we're only left with two possibilities. One, that there's stable crack growth, right, DADN, and there's some slope to that plot we'll use. Or this crack is already big enough that it's expected to have catastrophic failure already. Okay, but so that would mean the estimate of remaining life is like 0, right? So if they tell us we're to calculate remaining life, there's probably some life remaining. And so the first thing we're going to do is just double check that this thing meets the criteria for a thick specimen that we can use plane strain assumptions. So we had this criterion that said the thickness of the plate, B, and in our case we'll check the 0.5 inches, has to be greater than or equal to 2.5 times the plane strain fracture toughness K1C divided by the yield point, and that has a square on that term. So we can plug these things in. We get 33.8 divided by 84.5 squared. So that's a little less than half. Square that, you get about 1/4, and then we'll multiply that times 2.5. So we'll get about, oh wait, no, that would be less than 1/4. Hang on a second. Oh, my math was wrong. So it's much less than 1/4. So anyway, if we do this math, we come up with 0.4 inches. So our plate is 0.5. So we can use plane strain formulas here. So we don't have to correct and make it a plane stress problem. If you don't know what I'm talking about, just take my word for it. It's going to help you on the problem set. So this is how you check to see if you can use plane strain approximations or not. Is that thickness there? So we can move forward. So the first thing we can do is just like a dummy check. Is this crack already critical length that's going to propagate? So hold on. All right, I need a blank slide. Okay. So we can write an expression like this, right? So failure, in this case, fast crack propagation is expected if our situation surpasses the plane strain fracture toughness K1C. So our situation is going to be some kind of a geometric factor, we'll call it C1, times our maximum stress that's being applied, times square root pi A, where A is the crack length in this situation. So we can calculate this maximum stress if we know the load and we know the cross section. We were given some crack length A, and so the last thing we need is this geometry factor here. And that geometry factor is a function of the width of the plate and the size of the crack with respect to that. So I'm going to show that plot on the next slide here. And this slide is, or this chart is taken from the textbook in chapter 3. And so this is for an edge crack, and it's for mode 1 opening of an edge crack. And what it is as a function of A over B. So our A over B, right, is going to be the crack length divided by B, which is, say again? 10. Is that how it's defined in the first schematic? Or is it half that? Yeah, 10, okay. So it's quite a small number. And so we look at that on the x-axis, and then on the y-axis is C1 times the quantity 1 minus A over B, and that term to the 3/2 power. So we still have to solve for C1 even after we read this number off the chart. And if you look at the chart a little bit more closely, you're going to see that on the y-axis here, this correction factor is pretty small. So for all values of A over B from 0 to 1, which means no crack to the crack goes all the way through, this quantity on the y-axis basically goes between, 0.97 at the minimum and then 1.122. So it really is a very small change there. And so the book is sort of quick to point out that regardless of how big the crack grows, our C1 is not really going to change that much. So in our case, A over B, pretty low, kind of over here-ish, right? So we can read off 1.05. And if we solve that out, comes to about 1.11. So it's not really too much of a factor. And they point out that if the crack grows like really, really big, so we don't know how big it's going to grow to be critical. That's what we're kind of checking right now. But let's say that it grows up to like 0.3 inches. So it's more than 3 times that length. What is the C1 in that case is 1.13. So it's the change is only in the hundredths place. So we're just going to use the first one and move forward from there. So let's go back now. Okay, so C1 is 1.11. The maximum stress is going to be 160,000 pounds divided by 10. And we can subtract off the crack length if we want here, but it's quite small, times 1/2 inch. And then square root of pi times 0.075. All right, so what do we come up with? And let me just write down the K1C, which was 33,800 pound square root inch, no, PSI, square root inches. So I didn't actually do this math, but if anybody gets the answer, let me know. Let's see. I think I got something wrong. Okay.
I got like 59. The figure.
Say one more time.
I got like 59.
59.
KSI equals square root of inch. Like significantly more than the K1C.
Yeah, that doesn't make sense to me, so I'm trying to figure it out here. What have I done wrong here? This was supposed to be the easy example. Go back here. See, this crack size should be very small compared to the critical crack length. 33.8. Did the math twice. Give me 1 second here. You guys figure it out?
Zero. Yeah.
The actual at the tip is about 17.
No, I got a zero. That's fine.
Say it one more time.
Yeah, I missed a zero.
17.37 KSI.
Ah, okay, yeah. I don't know how I did it wrong twice in a row, but I just got 17.24, so that's right.
We forgot to put a zero in the .075.
Oh, yep, that'll get you. Okay, good. So the world continues to make sense. Okay. So this turns out not to be true. So our crack is not of sufficient size to cause catastrophic failure. So that means that this thing can continue in operation, and it should experience steady crack growth until it reaches some critical size. So what will be that critical size? Well, all we did in this was we plugged in all our numbers and checked it against the K1C. And so if we leave the crack length A as a variable and solve for that, then we can figure out what our critical crack length will be in order for it to cause catastrophic failure. So we can take that equation we had on the top, this one here, and solve it for A. And we come up with 1 over pi, because those are both under the radical. And then the quantity, K1C, divide by C1 times the maximum stress. And that would be squared. Okay. So we can plug that in. This math is already done for us. 33.8 divide by 1.11. And the stress comes out to be 32,000 psi. So I'll just write like 32 kpsi. That's already in those units. And this comes out to be 0.28 inches. So we have a long way to go. Was there a question? Yeah.
Does C changes with A?
Say one more time.
The C1 time doesn't it changes with A, right?
Yeah, not a lot.
C1 does change with A, but not a lot. So that's why I showed that plot with this here. So, okay, so if A goes out to that value, then it only changes by 1/100th.
C1 also does not matter.
So in this problem, they actually use the nominal value. They just use 10 instead of 10 minus 0.075. But the stress would increase, so you could tweak the equation to be a little bit more accurate. If you did, 1 second, Ryan, if you did the stress instead of 160,000, right, you could say the area would be 10 minus A times 0.5. And so as A grows, stress will grow. And then you would probably get a value that is, a little bit smaller, right? A little bit more conservative and a little bit more accurate. Mm-hmm. Question?
The CI.
Yeah.
I got the 1.11.
Mm-hmm. Yeah, so I did it for the initial crack length, which was like 0.075. So it's this, it's right here on the x-axis. And so that would be about 1.05. So we equate that to what it says for the y-axis. So there's this expression that's a function of CI, and then we equate it to that. That's how we get CI, or C1. It's kind of a roundabout way of doing it. They could have given a plot of just C1 versus A over B, and that would have been a lot easier. But I think that that 3/2 power, something with the convention of the way it was done in the past, some of the geometries have a power of 1 there. Some of them have 3/2. So. So I solved this equation for the C1. So if we take our A over B, which is 0.075, and plug it in here, and then we could even just compute that value and then divide it into the other side. Does that make sense? Okay, cool. Okay. So we're going to move forward with that value, even though we could get something maybe a little bit smaller if we more accurately accounted for how the CI is changing and how the stress is changing as the crack grows. Okay. So how do we then go from this 0.075, which is our current crack, up to 0.28? Well, we follow this chart that was given to us, and I know it's really small here, in the book, which plots the crack growth rate per cycle versus the change in the stress intensity factor range. Okay, so this was the way that was found to normalize all of the data for, and this is specifically for the nickel, molybdenum, vanadium steel alloy that we've been talking about. And so it was tested under many different loads. And so with the same crack length initially. And they found that the crack growth rate all collapses onto one curve if they plot it as this change in stress intensity factor versus the crack growth rate. So we're going to use that. And they have a slope on here that says dAdN is equal to 1.8 times 10 to the minus 19. And I say slope because this is a log-log plot. So everything that's shown as a line on a log-log plot is not actually the equation of a line, it's a power equation. That's why we have this here. And in this case, it's a power of 3. So this is our independent variable, delta K, what was changed by changing the load. And then that, if you cube that and multiply it times a constant out front, then you can get the crack growth rate, dAdN. Okay, so how can we set this up to solve our problem? So we have an expression for how this delta K is changing. And so we are going to equate that with this expression here. And we're going to plug that in. So then we'll have dAdN is a constant times something that's a function of A times to the third power. Okay? So let's go find an empty slide to work on that. Okay. Here we go. So I'm going to write dAdN is equal to 1.8 times 10 to the minus 19 times the quantity, C1, stress, square root pi A, and all of that to the third power. Okay, so now we get to do some math, right? Because we have a rate of something, we have the crack length changing with n, And then we also have a function of the crack length in here. So we're just going to do an easy separation of variables and then integrate both sides. So first what I'm going to do is take everything with a to the left side. So I'm going to write dA divide by a to the 3/2 power, because it's under a square root to the 3rd power, so that's 3/2. And then we take it to the other side, so we divide. So far, so good. We'll put everything else on the other side. So we still have our constant, 1.8 times 10 to the minus 19. And then we have C1 sigma square root pi, and all that is to the 3rd power. And then we are missing our dn, so this side will integrate with respect to n. There's no n's in the equation, so that side will be very easy. Okay, so let's integrate both sides. So we can just draw an integral on both sides like that, right? Or we could even draw this side as the constant out front and then just integrate dn, since there's no n in the function. But what are the limits on this integration? Well, luckily we have a, and we know the beginning and end of a. So we are going to integrate a from 0.075 up to 0.28. And I'm just going to just draw like some little marks in here so I don't have to rewrite this entire equation. And then we'll have our big constant out front on the right side, and we'll integrate from 0, which is how many we could have remaining, up to the number that we do have remaining. Let's call it NF, some final or failure number of cycles. And then the same expression there. So those are our limits. So it's super easy to take this integral, right? So we write it in brackets. So we can write this left side, we can think of it as a to the minus 1.5, right? So if we just take the integral of that, we add 1 to the exponent and divide by the coefficient. And so we come up with, it's like minus 1/2, and then we just get square root of a here on the bottom. And we do that from 0.075 up to 0.28. And that equals our whole expression on the right side times, or from 0 up to NF. Right? And here is just, we just throw an n in there because we didn't have anything there before. Integrate, now we have it there. Okay, so I'm going to go to the next slide. Any questions up to this point? Yes?
Sigma has two values, right? Min and max, 0 up to 160.
It's fluctuating, that's true. Mm-hmm.
And then how it is incorporated in this form? Like sigma, it looks like it's a constant.
Right. So it is, it's not incorporated explicitly in this formula, because this formula that we have is for even for like a static load, right? And so in this case, the because we haven't used the SN curve at all, right?
But if it's a static load, then there would be no n, right?
Correct.
Because here it goes from 0 to something, but if it goes from some value to some values, then there has to be some sigma, right? Because here is 0, the minimum is 0, so we don't care because n would be 0.
Right. Right.
But if it goes from certain value to certain value, then there are two sigmas, right?
I mean,
There are,
less intense sigmas probably not going to be what causes the crack to fail.
so the question is, why are we using this expression for the this sort of fracture toughness type term here, when that term does not have some expression that accounts for the fatigue aspect of this, right? Because there's, right, we have like sigma mean, sigma max, right? All of these things that we had been calculating, right?
Because that formula is delta K, right? So the one part of the delta K is 0, that's why I think we just use that one. If there was sigma 1, then it would be like C1 sigma 1 root pi A minus C1 sigma 2 root pi.
Ah, yes, okay. So you answered your own question, I like this. So we substituted that in because we had a change in this term here, right? So it's a change in that term, and it's the maximum change, right? So we're going from 0 to 160, back to 0 to 160. So that's the change that we get. Okay, good. Okay, so now we can plug in some values from the integral here. So we'll say, I think I should have had a -2 out in front of them instead of a -1/2. Give me 1 second. Let's change this to a -2. Sorry about that. Okay. So the left-hand side, -2 divide by square root of the larger value, 0.28. And we subtract off the smaller value, but it's a negative, so 0.075. That is going to be equal to our entire right side. So let me write it out here. 1.8 times 10 to the minus 19 times 1.11, or 1.1. Well, we can use the higher value now. 1.13 times 32 k psi, that's the stress, square root pi to the 3rd power times NF. And all of this comes out to be 4.47 times 10 to the minus 5. Okay. So we can put in the math here, and it comes out to be minus 3.78 plus what I did not write down. It's 6 something. Okay, sorry about that. It's 6 something. And so this side comes out to be 3.16, okay, is equal to 4.47 times 10 to the minus 5 times NF. So now we have one equation, and we can solve for NF. So we come out with, that's not the right number, hang on a second, this should be 3.5. Get too many things on the same.
7.2, the other one, so 3.5.
Say one more time.
Yeah, 3.5.
3. You got 3.58? Or I got 3.52, but it's close enough. So if we solve that, we get 74,324. Okay. So that's, hang on 1 second. So that's how many cycles we can get further before we would expect the crack to reach the critical crack size, and the whole thing fails. So what we've done is we've accounted for nonlinear crack growth here by using the change in by using the growth rate and solving the problem, instead of just maybe solving for the growth rate at one particular size and then having to iterate back and forth. So we've solved it in a much more efficient fashion. So I told you that this problem, I was going to solve it 2 ways. So we've already solved it this way, and then the book gives us one more idea, which is to account for the plastic zone. So to make a plastic zone correction, and not just assume that we stay in linear elastic zone the whole time. And so this is this is also on the problem set, right? If you've seen this term before, right? So we can have a plastic zone radius that we can calculate based on geometry and some of the material properties. And that comes out to be a length, right, that adds on and gives us a little bit longer of an initial crack size, because we're assuming that the plastic zone is not able to take more elastic stresses. It's already yielded, and so it's no longer in linear elastic fracture mechanics. Okay. And so we'll do that, and then we'll get a little bit of a larger length, and we'll see how much that changes how many cycles we have left. So we can write that the radius of this plastic zone correction is 1/6 pi times the plane strain fracture toughness divided by the yield strength. That's kind of why we were given that at the beginning. And so if you plug in those values, we get a very small correction, which is 0.008 inches, but it's not that small when you consider our crack size was only 0.075 inches. All right, so that's more than 10% change. So if we take our initial crack size and we add on this plastic zone correction, we'll call it A prime, then we come out with 0.083 inches. So that's what you'll see in the example problem in the book. I wanted to do the simpler case first before we came back and did this one. And so the solution is exactly the same, right? Except now instead of integrating with the 0.075 inches as our initial crack length, we have a new initial crack length of 0.083. So we should get a shorter lifetime if our initial flaw is already a little bit larger, right? Because we've lost the number of cycles that we could have had between 0.075 and 0.083. And we could calculate that as well if we wanted to. And so all we have to do is go back and change what's in our integral. So if we set it up, on the left side was -2 divided by our critical crack length, 0.28. And then all we do is add this, instead of 0.075, it's 0.083. And then the right-hand side is the same. So instead of 3.52, we come out with 3.16. And that is equal to this side, 4.74 times 10 to the minus 5 times NF. And the number of cycles we could get is 66,700. Okay. So before we got 74,000. So that little bit really cut off quite a bit of cycles, like 8,000-ish cycles out of 66,000. So an eighth of the life. Right, so it's not insignificant. And so if there is a plastic zone there, we can make that correction. And then based on the other questions from prior, we could make this a little bit more accurate by taking into consideration how the maximum stress is changing as the crack grows, and then also how that C1 is changing as the crack grows. And so does that kind of make sense? Yeah? Okay. So the next part is a little bit more interactive for those who are here. I have printed out the the stress time pattern for problem 22 in the end of the book. And so if you are watching this lecture, you're welcome to stop and make sort of a sketch, if you want, of question 22. And I'm going to pass this out. Can I ask you to take one and pass it that way? Be awesome. Here. Yeah. Could you take a few and then just pass them? How many more? I think. Do you have enough? Okay. All right, so this is a pretty straightforward problem. And so I gave you the stress time pattern. And I have the same thing shown up here on the screen, but I sort of grayed out the bottom part of it. And that's because it's the same pattern repeated. So one block is just that initial pattern. So we don't have that much time left in class. We only have like 5 minutes. And so I'm going to go ahead and just say for the next few minutes, just draw the rain flow on here. And then maybe in like 3 or 4 minutes, I'll just close out the lecture by talking about how many I counted. And then I'll finish the problem at the beginning of the next lecture. So take about 3 minutes and just try to draw the rain flow as you see it. Okay, so it's been like 3 minutes. So hopefully you had a chance to give it a try. You okay? You got 5? Okay. So people are volunteering how many they got. Okay. So 5, 10. Do we have any confirmations? Anybody else?
That half is 5, yeah.
Wait, you did the whole thing or just one block?
Whole thing is multiplied by 12.
Ah, okay. Mm-hmm.
I did the top block.
Top block is 5, yeah.
All right. Anybody else in the class want to volunteer what they got?
Yeah, I got 5.
You got 5? Okay. So consensus seems to be 5. And so I agree with that. So there's 5 total cycles of stress reversals in here where it goes fully up and back down. They do not all have the same amplitude and mean stress, but there are 5 complete reversals of different amplitudes in here. So if I start at the top, sort of right inside here, I can come down and do my first rain flow left, and I'm going to stop at the bottom there. So I can call that like path number 1. And then if I want to, give me 1 second. That goes from 0 down to minus 50. And then if I look right inside at the end here, I've got another path that comes down and is the same distance, right? So if I call that path 2, those both go between 0 and minus 50. So that's considered one cycle, right, with a maximum stress of 0, minimum stress minus 50, which means the amplitude is 25 and mean stress is minus 25. Does that make sense? And so I agree with that. And I have 1 more minute here, so I'm just going to finish drawing the rain flows. So this one comes down, down, goes down here. So we get some little ones in here. This one comes down to here, and that one. I think I got them all. Yes, so if you go back and forth, you should count 5 full reversals. And if you want to do homework for this for the next lecture, make a plot of, or make a chart where you try to list at least the amplitude and the mean stress for each of these 5 fully reversing cycles. And then you'll be able to dive right in at the beginning of the next lecture. So we will end there, and I'll see everybody on Thursday.